In this video, we'll do a very quick review of the cross product of two vectors. We'll start by reminding ourselves that the cross product takes two vectors, vector cross another vector, but the result, unlike the dot product, will be a vector. So two vectors go in and one vector comes out when we do a cross product. We'll first define it geometrically and then remind us how we compute it in terms of components as a determinant and do a calculation. So I have my two vectors u and v. I'm assuming that my two vectors are non-zero vectors and that they are not parallel to one another. So something like I'm seeing in the picture here. If one of them is the zero vector, or if one of them is parallel, if they are parallel with each other, then their cross product will just be the zero vector. But let's think about the generic case where they're not parallel to one another. They live in a plane together. They form a plane. You can imagine a two-dimensional plane that contains those two vectors. And there is an angle between those two vectors that I'm going to call theta. I'm going to take my right hand and I'm going to point the fingers of my right hand along the vector u. And then I'm going to curl my fingers through the angle theta, and my thumb will point up in this picture in the direction determined by this vector here that I'm calling n. So what I'm doing is I'm using my right hand to determine one side of the plane. I started with my right fingers along u, I curled my fingers towards v, and my thumb stuck up above the plane in the direction of this vector that I'm calling n. N is a unit vector, and we'll call it the unit normal to the plane, and it's chosen by what's called the right hand rule. I started with u, I curled my fingers towards v, and my thumb sticks up above the plane. If I started with v and curled my fingers towards u in the opposite direction, my thumb would point downwards instead. So n will determine the direction of the cross product, and I need to tell you the length of the cross product as well. So the length of u cross v is going to be the length of u times the length of v, and unlike the dot product, which had the cosine of the angle between them, we're going to have the sine of theta. That's a scalar quantity right now. It's the length of the cross product. And to make this a vector, u cross v is defined to be the scalar quantity times this vector n, which is chosen according to the right-hand rule. So this much here is the length, and then I've made it a vector now by scaling my unit normal vector, my length 1 vector, by this amount to get a vector that is sticking out of the plane. So here's u cross v, and it's pointing in the direction of n, and its length is given by this sine of theta quantity. To get a better understanding of the length of the cross product, let me redraw my two vectors lying flat on the blackboard now. Here's u and v. They form a parallelogram, so parallel sides here, and I want the area of that parallelogram. So what do I need to do? I need to find the base of it times the height of it to find the area. The base is the length of the vector u here, that's the base of it, but the height is this vertical height at a right angle, and to do that I need to look at the angle between them. It's the opposite side that I want, so it's going to be the sine of theta, and I've got to multiply that by the hypotenuse of this little right triangle here, which is the length of v. So the height is length of v times sine of theta. And this is exactly how we've defined the length of the cross product. So geometrically, this is very nice here. The cross product is this vector whose direction is chosen according to the right-hand rule, and whose length is the area of the parallelogram that the two vectors form. If those two vectors were parallel, or one of those vectors was 0, that area would be 0, and in fact the cross product is defined to be the 0 vector in that case. But when these two vectors are relatively orthogonal to each other, that area will be fairly large and the cross product will be fairly large. Now to calculate the cross product in practice, you do it in terms of components. So suppose u is equal to u1, u2, and u3, and v is equal to v1, v2, and v3. Some calculation, some proof will justify the following fact, and I'm not going to do that in this video because this is just a quick review, that the cross product U cross V is actually a determinant expansion. I'm going to take the determinant of a 3 by 3 array. The first row will be the basic vectors I, J, and K. I'll put my U vector components along the second row, U1, U2, and U3, and then V1, V2, and V3 will go along the third row. And this is a determinant here. You do a big expansion, and as you do that, you'll get the components of the cross product U cross V. So this is the component form of the cross product. Again, there is some proof required to get from here to this geometric formulation of the cross product, but we'll skip that here. So let's take some vectors U and V. U is 1, 2, 0, and V is -1, 1, and 1, and we'll find the cross product U cross V. As discussed above, it's this determinant. I'm going to put I, J, and K along the first row. The second row will be 1, 2, 0 for U, and V will be -1, 1 along the third row. We start expanding. You do the expansion along the top row of this determinant, and the first thing you're going to do is the I component. The I component you get by crossing out the row and column that I determines, and you look at the little 2 by 2 array here and you do its 2 by 2 determinant. So you go 2 times 1 minus 0 times 1. 2 times 1 will give you 2 minus 0, and that number will determine the I component of the vector. You then move to the J term. The J component will always get the opposite sign, so there will be a minus sign here as you do the determinant. And there will be a 2 by 2 determinant that goes in these parentheses here that you get by crossing out the row and column that J appears in. So you're going to take 1 times 1 minus 0 times -1, and you'll have 1 minus 0. You now move to K. You cross out the row and column that that appears there, and you look at the little 2 by 2 grid here, and you go 1 times 1 minus 2 times -1, and that determines the K component. 1 minus from the determinant and -2 from the sign that appears in the multiplication here. Simplifying this, we have 2I minus J plus 3K is our cross product. Or if you prefer, you could write that as 2 minus 1 and 3 with angled brackets. The order of the cross product matters. If you go V cross U and you do the right hand rule here, you start along V, you curl towards U on your right hand fingers, your thumb will point down now, and you'll have the opposite direction. And so you'll have the same vector but pointing in the opposite direction, same length. It'll be the opposite of the vector that we just calculated. We don't have to do the determinant again. We can just flip the sign of everything. It'll be -2, 1, and -3. Geometrically, this has an interesting interpretation. If I look at U and V, they form a parallelogram, and the area of that parallelogram now is easy to find. It's going to be the length of the cross product that we've calculated. And so we just sum up the squares of the individual components. 2 squared plus 1 squared plus 3 squared gives me 4 plus 1 plus 9, and take the square root of that to get square root of 14 units squared for the area of the parallelogram that they form.